Hi. Today we are going to discuss about observability standardization. And we are going to see what I call the elephant that I believe is still in the room. So a typical observability setup looks like this. So we have some kind of applications or systems that are exposing metrics. Then we have time series databases or logs databases where we centralize all our logs and all our metric data. And of course, then we have a tool to provide dashboards. This tool usually queries this time series data or logs data and creates beautiful charts. And then we have an alerting engine that again performs the same, so it queries time series data and sends notifications if something exceeds a threshold. Now, this has some issues and some complexity. It may sound simple, but there is a hidden complexity here. And this is what the hidden complexity is. In the time series databases, you have to maintain first the database server itself. You have to take care of the high cardinality and the memory requirements of that thing, the disk I/O requirements, and you have to think about clustering and high availability. In the logs database, you have the similar thing, but also on top of it, you have a query performance issue, so that in many cases, you have to maintain the indexes of the log streams that are available. You have to maintain retention, and you also have the same problem of clustering, availability, high availability, etc. Then on the dashboarding tool, you have to first learn the query languages of the other database servers, so that you can query them and create useful dashboards with the data they have. These query engines are usually good in order to convert, counters to rates or aggregate metrics together, correlate metrics together with some aggregation functions, pivot them, group them in a way in order to present them, etc. So you have to learn a query language, and you also have to learn what the visualization tool can do, what kind of visualizations you have available, what kind of customizations are there available. So in order to have, at the end, a meaningful monitoring solution. And something similar exists also, some kind of complexity exists also for alerting. So while building this, what you need is a deep understanding first of the metrics that you have. So you need to know what the database has and what labels are there, how you should query them. You need, in order to maintain this processing pipeline, you need to go through various steps of configurations in different phases. So in order, for example, to reduce the cardinality of some metrics, you may have to relabel some of the metrics at some point. You have to learn the query language the languages that we said. You need to understand the tools and have a very good understanding of the tools. And of course, you need experience. So if you don't know, if you have never done this before, most likely you are doomed. You need to have an understanding of what is a heat map, what's a histogram, how to visualize this kind of data. You need to have a lot of best practices in order for this to be actually useful for people while troubleshooting. If you are at scale, then you have additional problems. So you have to go through scalability challenges, how the database servers can be scaled, how I can have high availability there. You have to work on the data overload and the noise that may exist in all these dashboards, in all these alerts, etc. You have a cost management aspect that is important and you have to manage, because you may need at some point to cherry pick what you want, what you really want, what is really useful for you, because otherwise the cost of the monitoring infrastructure will skyrocket. And of course, you have to check also compliance and security. So you have to check what kind of information is in your logs and who has access to them and all this kind of stuff. If you're in a team, you have an additional layer. Then you have to come up with some kind of monitoring policies. You have to agree on a unified monitoring framework. You have to have some kind of change management and shared responsibility on the dashboards and the alerts and the data in general that are in these database servers. You have to take care of documenting everything and, you know, letting others know how this thing works, what they should do, how this needs to be changed, etc. And you need to have quite some discipline in order to follow your design principles always. Otherwise, it usually becomes a mess. So, to understand this, I asked ChatGPT to come up with a few phrases that actually they are the challenges, let's say, that these engineers that work on a monitoring setup have in their minds every day. What they usually think, what are the challenges they face every day. ChatGPT came up with this. So I made it a word cloud for us to see. So ChatGPT rate them with a frequency, how frequently each phrase comes up, and this is what it came with. So balance scrape interval, structure multidimensional query, test and validate queries, monitor exporter health, time series database I/O bottlenecks, dynamic alert threshold, regular expressions for label rematching, federation efficiency, fine-tune chart axes and scales, filter metrics in exporters. You see, it's all the details that people have to go through in order to have a monitoring, to build a monitoring with such a setup. Now, I also asked ChatGPT to tell me what people that are monitoring infrastructure are usually thinking of, independently of the monitoring system. So what people should be thinking in general when they are responsible for the performance and the stability and the availability of some kind of infrastructure. And ChatGPT came up with this list. Now, this list is quite different. Now it says incident response, application stability, data encryption, cost optimization, service availability, client satisfaction, operational efficiency. It's completely different. It's another level, actually. Now, this is what I think is the gap of the current monitoring tools. Most of our monitoring tools, most of the monitoring tools that exist today, force us to think like this. This is the challenges we face every day. How to do this little thing, how to create a heat map query for quantiles, how to configure external labels. These are details of the internals of the monitoring system, while the other list, this list, is what we need our engineers to think. This is their primary role. This is what they need to achieve. This is what they need to focus on. Now, some may think, okay, wait a moment, we have a lot of standardization bodies that are taking care of this. Of course, we do have, and we have, for example, OpenTelemetry, we have CNCF, we have W3C, etc. But you know what? If you actually check what all these standardization bodies do, is the following. Do you remember this chart, this graph that we started with? They focus here. So what they do, all our standardization effort is about data exchange. Is, okay, let everyone have all the data. If you need the data, okay, take them. But all the complexity that we have is outside this. Of course, this is an enabler. We need it. It's good to have data compatibility and being able to exchange data, because otherwise it's a lot more complex. But I think that the most important aspects of efficient monitoring are not there. So actually, we don't have any standardization. This lack of standardization is actually the shift, the major shift in our focus. So instead of improving our infrastructure, we spend most of our time in a sea of challenges around the monitoring itself, about how to achieve something with the monitoring system. Now, I also researched what analysts say. So for analysts, they have this DevOps role, the DevOps role, that is supposed to be the clue. It's supposed to fix the gaps in this thing. But now, what analysts believe is that the DevOps guy, is a data scientist who understands software engineering and is an IT network architect at the same time. So he understands technology as a sysadmin, software as a developer, and data science as a data scientist. And it's a combination of these three. So what the analysts are saying is actually that there is a guy, or a girl, of course, that knows what is coefficient of variation, that knows what is IPC, instructions per cycle, and somehow can figure out if an application, a running application, production application, is memory bound or CPU bound, and at the same time can understand what is the disk utilization of an NVMe or an SSD disk, what's IOPS, and under which conditions such a disk, for example, can get congested. To my understanding, the whole thing is a utopia. So these people that can actually know data science, the vast area of data science, have huge experience in software engineering, and have vast experience in IT infrastructure and network architecture. In some companies, bigger companies solve this problem by having a lot of roles. So they have an army of people to take care of a few things, like the monitoring. But for smaller or medium-sized companies, and also for a lot of Fortune 500 companies that don't invest in this, this is a break point. So this kind of engineers that have all this magical knowledge, experience, and skills simply does not exist. Now, the result for all of us, the result for most companies is is something like this. So monitoring is very expensive and a constant struggle. So it's never complete, never finished, never okay, never enough, while being extremely expensive. We have, it requires a lot of skills, and actually for most of the companies, the quality of the monitoring they have reflects the skills of the engineers. So if they have good engineers, they have good monitoring. If the engineers are not that experienced, do not have that many skills, then the monitoring is a toy, is a joke. Frequently, we see even in very big companies that monitoring is severely under-engineered. So it's next to zero. They have some kind of visibility on the workload, but that's it. This is where it starts and then it ends. And it's frequently illusional. And I say illusional, I was the first to experience this. So before I built netdata, I spent quite some time in monitoring, and I had quite some money and time and effort in monitoring, and I had built a great team. But at the end of the day, I had the impression that everything that I have built, all the dashboards and all the tools and everything that has been installed, is there just to make me happy, because I cannot troubleshoot anything with it. It's not useful for what I needed. So in many cases, I still see this today with many companies that we cooperate with, that the monitoring gaps and the and it leads them, the monitoring inefficiency leads them to wrong conclusions, to increase their time to resolution, a lot of frustration, a lot of issues, etc. Lost money, of course. So now I'm going to talk to you about netdata. Netdata is an open source tool that provides opinionated observability. So the idea of netdata was to solve all these problems that we saw so far. The idea of netdata, let me tell you a few things. So the first thing is that it was born out of a need. So I needed the damn thing. I had problems, I had issues with some infrastructure, and I couldn't solve them. I spent quite some time there. The problems remain. So after several months of frustration and lost money and lost effort, I decided that I should do something about it. Since the monitoring tools that exist today, they are not sufficient enough for this kind of job, then we need a new monitoring tool. Initially, it was out of curiosity. So I said, okay, let's build something. Let's see if we can build something. Because I couldn't believe that all the monitoring tools have this design out of, accident. So I was thinking that, okay, they tried different ways, and this is the only way that actually worked. So it was curiosity, why they didn't do monitoring real time, why they don't ingest all the metrics, why cardinality is such a big problem, why they don't, monitoring systems don't work out of the box, they don't come predefined with the dashboards and the likes that we all have, etc. So I started building it, and after a couple of years, I released it on GitHub. It was on GitHub from the first day, but I actually pressed the button to release it. Anyway, nothing happened. It was a funny story. Nothing happened. So one day on Reddit, I posted, and boom, it skyrocketed. So the netdata way says that we all have a lot in common. So my infrastructure, your infrastructure, their infrastructure, we are using the same components, the same parts of a Lego. So we are using the same or similar physical and virtual hardware, similar operating systems. These are finite sets of stuff. It's not infinite. The combinations are infinite, so we can combine these Lego things, these building blocks, the way we see fit. But all the building blocks are pretty much packaged. Today, even for custom applications that we build ourselves, in most of the cases we use standard libraries, and these standard libraries expose their telemetry in a standard and predictable and expected way. So even for custom applications today, this becomes increasingly true, incrementally true. As time passes, even these custom applications will be completely packaged, like packaged. They will provide a finite set of a finite and predictable and expected set of metrics that we can all consume to actually say if the application is healthy or not. Of course, there will be common metrics, custom metrics all the time. So we have a lot in common. The next thing is that I wanted high fidelity monitoring. High fidelity monitoring means everything collected every second, like the console tools. So my original idea was to kill the console for troubleshooting. What most monitoring tools provide is a helicopter view. So you can see that the road is congested. You can see the dive or the spike on that thing, but you cannot actually see what's happening. Why is that? This is a helicopter view. So this happens mainly because they want the minimum, including commercial providers, including companies that provide monitoring solutions as a service. They do this because it's expensive to ingest all the information. So they prefer to select the information, which information to ingest and maintain, so that you can have the helicopter view that you need. But once it comes to the actual details of what is happening there, why this is happening like this, they don't have any information to help. And this is where the console tools usually come in place. So with netdata, I wanted the console tools, I wanted to kill the console for monitoring. So every metric that you can find in console, it should be available in the monitoring system without exceptions, even if something is extremely rare or is not very common to be used. The next thing is that I wanted all the metrics visualized. So I don't, come on, it's an Nginx, it's a database server, Postgres. I don't want to configure visualization for this packaged application myself. Why to do that? It exposes workload and errors and this and that and tables and index performance and whatever it is, but I want this visualization to come out of the box. The next is that I didn't want to learn a new query language. So I wanted to have all the controls required directly on the dashboard to actually slice and dice the data the way I see fit. So in the data, we have added a nice ribbon above every chart that allows you to filter the data, so slice the data by label or by whatever node, instance, whatever it is there, but also to group them differently. So it's like a cube to see different aspects of the cube. And of course, we added unsupervised anomaly detection, and this is an innovation we have among all the other monitoring solutions, mainly because our anomaly detection happens for all metrics unconditionally, and it's totally unsupervised. So you don't need to provide feedback to it. This is what unsupervised means. You don't have to train it yourself. Also, it is trained at the edge. So we don't train somewhere what a good Postgres means and actually give you the model to apply it to your database server. You will never, it will be full of false positives, mainly because in monitoring you have the workload that determines, the actually queries that you send to a database server determine what the metrics will do. So it's impossible to learn to share models. The only viable solution is to train models for each metric individually. And out-of-the-box alerts. For alerts, what I wanted is to actually have predefined alerts that once they see a network interface, they attach to it. They see a disk, they attach disk alerts attached to it. They see, I don't know, hardware sensors, they attach to them. They see a Postgres database, they see a web server, they attach to them automatically. So netdata today ships with hundreds, actually we counted a few days before, it is 344 distinct alerts that are all dynamic, so there are no fixed threshold there. There are all of them rolling windows, etc., etc. So they compare different parts of the metric to understand if it is if there is a big spike or a big dive or an attack or something wrong. And of course, there are plenty of alarms that are just counting errors or things that are mathematically, you know, even if there is one, there is an error condition of it, and the users need to be alerted. Now, netdata, I wanted also netdata to be able to be installed mid-crisis. So you have a crisis, you never installed netdata before, you can install netdata right there while the thing is happening, and netdata will be able to help you figure it out. You are not going to have the help of the anomaly detection because this thing needs to learn what is normal in order to help you, but netdata has a lot of tools, additional tools on top of anomaly detection that will help you identify what is wrong, correlate what is happening, find similarities in metrics, etc. It will also allow you to explore the journal logs directly on the servers. So all this is about removing the focus of the monitoring system, of what the monitoring system internals from users, and putting some extra knowledge into the tool. So unlike, for example, if you take Prometheus and Grafana, when you get them and you install them, they are blank. They cannot do anything. They are just a database server and the visualization engine. Great, they are great database server and great visualization engine, but there is no use of them if you don't go through the process of configuring them, setting them up, pushing metrics to them, etc. In netdata, the story is quite different. So netdata knows the metrics. It knows already, when we ship it, it knows how to collect CPU metrics, memory metrics, container metrics, database metrics. It knows how to, it comes with pre-configured alerts. So it knows how to visualize the metrics, correlate, and come up with meaningful visualizations. So the idea is that netdata is a monitoring out of the box. It's ready to be used. The internals of what is happening there and why this is like this and how to convert a counter to a rate and all this kind of stuff is already baked into the tool for each metric individually, including the monitoring of each component individually. So for netdata, when you have a disk, it's an object in netdata. It has their metrics attached to it, alerts attached to it. So we monitor infrastructure bottom up. We don't go helicopter view. We go down deep, we deep dive to the highest level we can. We monitor and set alerts at that level, and we start building up. So let's see. Because even netdata has a lot of innovations, even in deployment, for example. So netdata is an open source software. As I said, you can use it for free. So the software you are going to get is a monitoring in a box. So the moment you install the netdata agent, it's not an agent, it's not the same as an exporter in Prometheus. A netdata agent is like something like exporters, time series databases. So you have Prometheus, you have the visualization engine, you have the alert manager, and you have also machine learning and the likes, including logs, everything combined into one application. Now, this application is modular. So for each installation you do, you have the ability, of course, you can use it by itself. So you can install it on one server and use it on one server. So it has an API, it has a dashboard, you can see the dashboard there, you can explore the metrics, etc. But when you can build, I can show you this, you can also use them, so you have a number of servers, you install them, you install netdata on all of them, then you can use our SaaS offering to actually have a combined view of all of them. If you don't want that, you can use the same software, the netdata agent, as a parent. So in this parent, now this parent receives all the metrics in real time from all the servers. So all the other servers are streaming in real time to it. This server now can have all the functions of the others. So it can alerts for them, anomaly for them, visualization for them, everything required. This allows you to offload the other servers. So these extra features, let's say, take some CPU, take some disk space. So you can offload, if you want, the other servers and use only the parent. Of course, this is infinitely scalable. So you can have data centers, different data centers, or many places all over the world where you have infrastructure. You can have a parent there and then use netdata cloud to aggregate the parents now. Or you can have a grandparent. So you can have a grandparent or a grandparent. So it's infinite. You can scale it as you see fit, as your infrastructure grows. The whole point with this now is that netdata is a lot faster compared, for example, to Prometheus, and requires a lot less resources. So for netdata, we stress tested netdata and Prometheus. We set it up 500 servers with 40,000 containers. We had about 2.7 million metrics collected every second. And we configured actually Prometheus to collect all these metrics in real time also per second. And we measured then the resources that were required on this netdata and Prometheus. And the result is this: 35% less CPU utilization, so 1/3 less CPU utilization, half the memory of Prometheus, 10%, 12% less bandwidth, 98% less disk I/O. This is because we don't need a wall, so netdata doesn't write all the time. We rely on streaming and replication for high availability. So each of the parents can be a cluster. It's very easy. You just set them up in a loop. You can have 3 parents in a cluster, 4 parents in a cluster, and all of them are in a loop. So the idea is that instead of committing data to disk and trying to have something that can sustain failures on each server, we rely on replication and streaming to make sure that we will not lose data in case of failures. So 98% less disk I/O, and also on retention. So you see that in the data, we say there 75% less storage footprint, but actually it is actually a lot more. The problem here is that, no, the key characteristic of netdata is that it can downsample data as time passes. So it has tiers. It can have up to 5 tiers. We ship it with 3, but you can configure up to 5, where you downsample data from tier to tier. Now, netdata also is one of the most power energy efficient platforms out there. So last month, the University of Amsterdam did a research. We didn't know, we saw it when it was published, that netdata, they said netdata excels in energy efficiency, is the most energy efficient tool, and excels in CPU usage, RAM usage, and execution time when it monitors Docker containers. The whole study was about Docker containers. Let's move on to AI, to artificial intelligence, and what is there, what happens there. So in 2019, Todd Underwood from Google made this speech. This speech says that actually all the ML ideas that Google engineers had were bad. They couldn't have the expected outcome, so the engineers set some goals and they tried. They put them down and they tried to do it. But the goals were not there. It was impossible to achieve them. So all the ML's ideas are bad, and we should also feel bad, as Todd says here. Now, in the data, we have ML. Now, what we do? The first goal of machine learning in a data is to understand, to learn the patterns of the metrics. So we didn't want to, that's the first goal. Can we understand the pattern of the metrics so that the next time we collect a sample, we can know reliably if the collected sample is an outlier or not. And we wanted this unsupervised. So we didn't want to do, to provide any feedback to the training. We train at the edge or as close to the edge, so you can train at the parents if you want. But the whole point was to understand if we can have a way to detect if a collected sample, just collected sample, is anomalous or not. And I think we have achieved that. So netdata trains 18 models. It learns the behavior of each metric individual for the last 57 hours. This is 2.5 points, let's say. It detects anomalies in real time. And all 18 machine learning models need to agree. This is how we remove the noise from ML, because it's noisy, it has false positives. So all 18 models have to agree that a sample is an outlier in order to say that it is an outlier. And we store the anomaly rate in the anomaly, in the collected data, together with the collected data in the time series. So it's like anomaly rate is an additional time series for every other time series. It's like having all the time series twice, one for anomalous, not anomalous. And we also calculate a host level anomaly score that we will see how it is used. Now, in netdata, one of the innovations we did in netdata is that we added a scoring engine. A scoring engine tries to score the metrics, tries to understand, given some parameters, it tries to understand which metrics out of the thousands or millions of metrics available are the more relevant to the query we do. So it can do scoring based on two windows to find the rate of change. It can score based on the anomaly rate. So which metrics were the most anomalous from that time to that time. We have also metric correlations that tries to correlate metrics together, so by similarity or by volume, so it tries to understand how the metrics correlate together. Now, let's see how this appear in a data dashboard. And a data dashboard is like this. It's a single dashboard, one chart is below the other, infinite scrolling, hundreds of charts. Of course, there is a menu here that groups everything into sections so that you can quickly jump from section to section and see the charts. Now, this dashboard is fully automated. You don't have to do anything about it. Of course, if you want to cherry pick charts and build custom dashboards and change the visualization, all this is there. But the whole point is that we wanted all of it to be, every metric to be visualized in a fully automated way. Each chart we will see has a number of controls. So the charts that you see in the data are a little bit different compared to the others. Let's go to that thing. The first thing is that when you are in this dashboard that you have, in this case, I think it says 590, 500, almost 600 charts in this dashboard. It says it here. When you are there and you can press this button, this AR button that's here, this is in Zoom, and netdata, what we'll do is that it will fill the sections with their anomaly rates. So for the daytime picker, from the duration you want it will score all the metrics and figure out what's the anomaly rate for that duration for each chart within them and then for each section. This allows you to quickly spot. So if you have a problem and you want to find, you don't know what it is, you have a spike or a dive on a web server, something is wrong, you don't know even what is wrong. You can just go there and hit that AR button and the data will tell you where the anomalies are. So you will be able to immediately see that, oh, my database server, my storage layer, or an application is doing something, has a crash or something. Now, this is a data chart. And a data chart looks like all the charts out there, but not quite. So the first thing that you will see is that there is this anomaly ribbon. The anomaly ribbon is this. This purple color indicates on the top the anomaly rate of all the metrics that are included here. In this case, the metrics are coming from 7 nodes, 115 applications, and there are 33 labels there. So the entire, all of them together, the anomaly rate, the combined anomaly rate is visualized here. Of course, you can have individual anomaly rate like this. So if you click the nodes, this model comes in. It has the 7 nodes one by one. It says how many instances, how many components. If this is about disks, this is disks. If this is applications, these processes in this case. So how many applications are there? How many metrics are available? What's the volume, the relative volume? So in the chart that you see, some of them contribute more than the others. This is sorting by the volume, a sorting by anomaly rate. If there are related alerts to context switches, in this case about applications, you would see them here. And you can see the minimum, average, and maximum value per node for this kind of data. The same happens for applications, for dimensions, or for labels. So it's a similar model that shows all applications in a list where you can see the volume, the anomaly rate, the minimum, average, and maximum, etc. And of course, you can use the group by. Oh, sorry, I didn't tell you that you can filter from here. So if you want to include or exclude something, you can just include it or exclude it here, and it will automatically change the chart. So similarly, you can use the group by feature to change how data are grouped. So you can group by node, you can group by application, you can group by dimension. In this case, it is reads or writes or whatever it is. You can also group by any label, whatever label is there. And actually by combinations, 2 labels, 3 labels, nodes and labels. So you can do all the combinations and group the data, see the different aspects of the data from this menu. Now, this menu is standard on every chart. Then we have the Anomaly Advisor. Anomaly Advisor is a tool that we developed in order to find the needle in the haystack. So you have a problem, there is an anomaly, we show this AR button that you press it, and you can actually see the anomaly rate of each section. But how can I find the individual metrics or the most anomalous metrics that exist for a given time frame, current or past? So we use the host anomaly rate. The host anomaly rate looks like this. So this is a chart. You see here that it is a percentage, and it shows the number of metrics of the host, of each host. These are hosts here, of the nodes. The number of metrics in the node that are concurrently anomalous. You can see that when you have anomalies, they are widespread. So you see a lot of metrics in that node become anomalous. So if there is a stress on the database server, disk will have increased I/O, CPU will be a lot more, probably network interface will have a lot more bandwidth. So all this combined together with all the individual metrics that we check, like the containers and the page faults, how many memory processes allocate, etc., or the context switches, or whatever happens, even interrupts, how interrupts are affected in the system. So all this information comes together and is aggregated here to see a huge spike when something anomalous happens. Now, when something anomalous happens like this, what you can do is highlight this area. So there is a toolbox here that you can highlight this area, and immediately Netdata will give you a list of all the metrics sorted by relevance for that highlighted window. So for that highlighted window, it goes through all the metrics, no matter how many they are. It scores them according to their anomaly rate, sorts them, and gives you the list in a sorted way. So you can see, for example, that the whole point of this is that in the top 10, 20 items that you have there, you should have your aha moment. So you should have, oh, someone SSH'd to this server. Or, oh, we have TCP resets. Something is broken somewhere else, and we have this, and this doesn't play. So the whole point is to have your aha moment within the top few items. Now, the way I see it, if I go through, is that the way I understand it is that we have really a lot in common. Our infrastructures under the hood are quite similar. We all deserve to have real-time high-fidelity monitoring. Solutions like Netdata keep up to this promise. So we spread Netdata like this in a distributed fashion, mainly to avoid the bottlenecks that all other monitoring solutions face. So netdata should be scalable better than anything else. Netdata Cloud, for example, is our SaaS offering. Today works at about, I don't know, less than 1% of its capacity, and it has 100,000 connected nodes. And it's just a Kubernetes cluster, not much. A small one, actually, a few nodes. So the idea is that we want monitoring to be high resolution, to be high fidelity, to be real time. We open sourced everything, so netdata is a gift to the world. And we open sourced even advanced machine learning techniques. Everything we do, all the innovations in observability are baked into the open source agent. And you know, even when you view one agent or a parent with 2 million metrics, the dashboard is the same. We don't change the dashboard, it's one thing. The same is the cloud. The data cloud has exactly the same dashboard as the agent. Monitoring, to our understanding, should be simple. It should be easy to use, easy to maintain. The data is maintenance-free, doesn't require anything. Of course, there are a few things to learn, how the tool behaves like this, and how I do streaming, how to build parent. You need to learn a few things. But even, you know, there is nothing to maintain in indexes. Most of the stuff are zero configuration and work out of the box. And at the same time, we believe that the monitoring tool should be a powerful tool at the hands of the experts, but a strong educational tool for newcomers. So people should be using these kind of tools like netdata to learn to troubleshoot, understand the infrastructure, feel the pulse of the infrastructure. And at the same time, we are trying to optimize it all over the place. So we want netdata to be a thin layer compared to the infrastructure it monitors. It should never become huge. This is why we want it to spread over the infrastructure, to utilize the resources that are already available and spare. Netdata on a single node requires just 5% of a single node utilization, of a single core CPU utilization, and about 100 megabytes of RAM. So we want this to be extremely thin compared to the whole thing, so that it can be affordable for everyone. Thank you very much for watching. Try netdata and see you online.